All right, chapter 5. We're working in chapter 5 on trigonometric identities. And we've looked at a couple of sections so far. And now we are up to 5.3. And so in this case, we're going to introduce some more trigonometric identities, but these aren't the fundamental ones that we've been working with up until this point. We have some specific new identities designed to help us accomplish things in trigonometry problems. And so let's take a look at what we have here. Like we have a difference identity for cosine and a sum identity for cosine. Those are the main identities we're going to look at in 5.3. We're going to look at some cofunction identities that it follows up with as well, which are not as new or interesting. Some little formulas, but we kind of already have formulas for. And then, of course, once you have the difference and sum identities for cosine, then you can look at applications for those as well. Okay, so but this difference and sum for cosine identities are very important. And in 5.4, we're going to look at the same things for sine and tangent as well. So that's basically our goal for the week, to look at the sum and difference identities for sine, cosine, and tangent. And we're beginning with the cosine sum and difference identities in 5.3. So that's the plan. All right, so they've got a couple of slides here to try to sort of work through the support or the idea of how they come up with the identity. But I think more important for us to focus on in the time we have in these not too long Zoom sessions, we want to look at what the identities say and how to use them. So I'm going to pass over these slides where they're basically justifying where the identity comes from. They're doing some work here, doing some calculations. And then they kind of solve, and they get down to this thing on the bottom here, right there. And when they've solved for cosine of A minus B, this is basically giving us an identity or a formula for how we can calculate the cosine of the difference between two angles in terms of the cosine of those individual angles themselves. So this is, as it says on the top, this is the difference identity for cosine. Then they go into the sum identity for cosine, which basically would be what you'd have if you have a plus there instead of a minus. And they spend a couple of slides showing how to get that as well. So let's skip over those, and then we'll put them together to take a look at them more carefully. So they're saying, all right, well, what if we had a sum? We could use the difference one and put in a minus, and how would that change things? And this is the summation that we want to begin with today. So here we have a cosine of a sum or a difference of two angles. So remember, A and B are going to be some angle in degrees, or they actually could be some angle in radians. And we could try to see what this says and check it ourselves by evaluating to see that whether it makes sense or not with angles that we know, for example. But we're going to see this in action a couple of different ways. So let's just examine with or explore this with an example. Let's say I wanted to evaluate the cosine of, we'll say, 30 degrees plus 60 degrees. Now I'm choosing these angles because we, from our tables of values and our past work, we know the cosine of 30 degrees. We know the cosine of 60 degrees. And of course, if I add 30 and 60 degrees together, I get the cosine of 90 degrees, which we also know. And so this is a way for us to try to explore a little bit and see what the formula says is equal and confirm that it really does come out equal. So if I were to try to explore this particular application of the sum of the cosines, according to this first equation here, using the first one here, And when I have the cosine of A plus B, where A is 30 and B is 60, that should be the cosine of A, 30 degrees, times the cosine of B, which is 60 degrees, minus the sine of both of those. The sine of 30 degrees and times the sine of 60 degrees. And so if we evaluate each of these cosine and sine of 30 and 60 degree values, then we could do the arithmetic on the right. And then, of course, we can check to see if it makes sense with what we would have gotten on the left. So the 30-degree angle, if we think of the 30-degree angle and imagine a right triangle to help us evaluate some of these angles. So 30 degrees means you have a 60-degree angle here. And we may recall with a 30, 60, 90 with a hypotenuse of 1, that the short side is 1/2 and the longer side is square root of 3 over 2. And so cosine of 30 would be adjacent over hypotenuse. So that would be square root of 3 over 2. And cosine of 60, I could go up to the 60 degree and then adjacent is the 1/2 angle. And so 1/2 over 1 would be adjacent over hypotenuse. And then similarly for sine of 30, it's opposite over hypotenuse. This is all using the SUKOTOA. And so the opposite over hypotenuse would be 1/2. And the sine of 60 degrees would be going to the 60-degree angle. The opposite would be square root of 3 over 2. So now that I've evaluated each of these trigs of angles, then we can do the arithmetic. So I get the square root of 3 times 1 in the top, 2 times 2 is 4, minus the square root of 3 times 1 in the top, 2 times 2 is 4. So both of these come out the same, and I would get 0. And we can confirm that this identity does seem to hold for the angles of 30 and 60 degrees in this case, because I can go ahead and add those, and 30 and 60 is 90 degrees. And so this is one of our quadrant border angles. When we're at 90 degrees, you're straight up at the point 0, 1, and the cosine is the x value, which we know to be 0 at that point. So it does check, and this identity seems to work with a couple of simple angles that we plugged in, just to sort of see what it says and to confirm that it works with a simple example. But this is the idea that if we have a sum of angles on the left, that we can then evaluate, if we weren't able to add those and evaluate directly, then we could evaluate the pieces on the right. If we can evaluate cosine of A, cosine of B, sine of A, sine of B, then we can get the cosine of A plus B. Okay, so I could do the same thing for the difference, but let's see how they have us begin to explore this with their examples. All right, now let's see how bad the PowerPoints look. So now we're going to go back to having some of these mixed up things sometimes, but at least it won't close up. Oh, we have like nothing here. Great. Okay. But I need the program to at least function, and I can try to fill in the blanks. All right, so this is cosine of 15 degrees. So what we're going to recognize is that 15 degrees could be expressed as 45 degrees minus 30 degrees. That 15 degrees is the difference between two angles that we know the sine and cosine of. So I can express cosine of 15 degrees as the cosine of 45 degrees minus 30 degrees. And then I can use the cosine of a difference of two angles formula. Because then I can evaluate the cosine of the difference of those angles using cosines and sines of those angles, which, as we just said, we know. So this would then be the cosine of 45 degrees times the cosine of 30 degrees. I'm calling 45 degrees angle A and 30 degrees angle B, and I'm using the cosine of A minus B. And you may just recall as you use these formulas, but you can always look them up, that when you have the difference of the angles, you will do the sum in the cosine identities. And you'll first do both cosines and then both sines. So then I would have the sine of 45 degrees times the sine of 30 degrees. And so in this way, we can figure out the exact value of cosine of 15 degrees by using this identity property. So let me pause there and see if there are any questions about how I set this up in order to try to find out the exact value for this problem. Okay, so cosine of 40 degrees is square root of 2 over 2. So is the sine, so I'll just put that over there while I'm thinking about it. And then cosine of 30 degrees, as we looked at a minute ago, was square root of 3 over 2. And sine of 30 degrees is 1/2. And so we can now do a little bit of arithmetic here. And square root of 2 times square root of 3 is the square root of 6. And 2 times 2 is 4. So that's the left fraction. And on this right side, we have square root of 2 times 1. So that's square root of 2. And on the bottom, 2 times 2 is also 4. And this gives us a common denominator. So I can add up the numerators, the square root of 6 plus the square root of 2, all over a common denominator of 4. And so I can conclude that the exact value of the cosine of 15 degrees is the square root of 6 plus the square root of 2 over 4. And then just in case there was some forgetful algebra, to combine roots like that, or what are called radical terms, you need to have the exact same radicand under the root. So if you have the square root of 6 and the square root of 2, you cannot add those together. Those stay separate. Those are unlike radical terms. And so they just stay separate like that. But that's still an exact value. I could always type that expression into a calculator to get whatever level of decimal approximate accuracy that I would like. But until I do that, I leave it as is, and you can't really simplify it, and that's the exact value. So in the chat, it says, how would you use this method or methods to say using the calculator results? Not sure. How would you differentiate this from a normal question of what is the exact value of 15 degrees? I'm not sure what you mean there, Henry. The question here is, what is the exact value of cosine of 15 degrees? So what do you mean a normal question?
So when say cosine of 15 degrees, right, you can find it directly. So I'm thinking, if it's the case that you are asked the question, find the exact value of cosine 15 degrees, how would you determine whether to use this identity or like saying cosine 15 degrees equal a certain result, basically?
Equals what?
Let's say, currently, I don't know how to calculate like cosine 15 degrees, but I'm thinking I've seen it before, right? And I'm saying, how would you know that instead of, setting cosine 15 degrees equal to the results that you find, which is, let's say, using it on a calculator, say converting 15 degrees to radians and using that to replace, let's say, 15 degrees, how would you determine whether to use this particular identity, or simply writing like the results there?
Well, the answer won't be different if you're using an angle in radians.
Yep. So
Nothing, there won't be a difference there. So
yeah.
15 degrees in radians, right, is like pi over 12.
Yeah.
And pi over 12 is equal to pi over 3. I'm sorry, pi over 4. 45 degrees is pi over 4 minus pi over 6. Is that right? Pi over 6 is 30 degrees, I think, and pi over 4. And common denominator is 12. Yeah. So if I then put in for 45 degrees pi over 4 here, and over here I put in pi over 6, then I would get this exact same problem, and then I would get those exact same values, and I would get the exact same answer. So it doesn't matter whether the angle is in degrees or in radians. Either way, cosine of that angle is going to give you the same exact value answer.
Okay, so my question specifically is, would they say you should use this identity as in, I know it's written up there, so would they say you need to use that specific identity, or how would you determine, like as the person solving it, will you determine that I should use like solving it directly using like the radians you brought up, and using let's say like the identity? So there are two parts. How would you determine as the person solving to find, or in the case of if they tell you to, they will tell you specifically to use this formula?
I think you'll have a problem given just like the problem here is given, where they will just tell you find this value. And I think they will feel or rely on the idea that it's part of your job in learning how these identities work to realize what you use these tools for. So like imagine if your job is to remove a screw from some wood. If you need to do that, well, you have to look at what kind of a screw you have and then choose which tool that you would use. Am I going to use a wrench to do that? Probably not. I'm going to use a screwdriver. Which kind of screwdriver? So the identities and things like that that we're learning here are tools to do problems. And part of learning the proper use of a tool is when you need to use that tool instead of a different tool. So they're not going to tell you use this identity to do this problem, because then they're telling you how to do the problem instead of just asking you to do the problem yourself. But when we learn about a tool, an identity, something to learn, then we practice using it on the problems that make sense for that kind of an identity, so that we can see how it's used and how it helps us do problems. And then in the future, if a problem like this pops up, hopefully the idea is you say, oh, for this kind of a problem, I remember I have this tool that I can use, this identity, and that I can rewrite 15 degrees in terms of this difference and use the difference identity to evaluate the cosine of this angle, which is what this problem is trying to illustrate.
Understood.
So I think that is one of the big challenges anytime we learn new tools in math, is that you not only want to see them showing you what the tool can do, but as you were just asking, so that's a great question, you want to think about, well, how do I know when to use this tool? Obviously, if they said, hey, use this tool, that would be really helpful, but that's not the norm for most math problems. So for example, if you have a problem from algebra where you have to solve a quadratic equation, well, they don't typically say, use the quadratic formula to solve this problem. They just say, solve this equation. And then you have to recognize, oh, this is a quadratic equation, so I should use the quadratic formula to solve it. So part of what we want to try to do in this learning process is not only see how these identities do a problem, but think as you're doing that to recognize, oh, so if I have this kind of a problem, then perhaps that's the tool that I choose to do that problem. And so as Jimmy is pointing out, one of the things that'll help you in this case is that they are asking for the exact value. And obviously, if we didn't say the exact value, like if they were happy with an approximation of cosine of 50 degrees, well, then we could just type that on a calculator. Calculators will give us decimal values of cosines of any angle we want to very high level of accuracy. But that's not what's being trained about here, and that's not what we're looking at. So the reason they asked for the exact value is because they want you to be able to produce an expression for the exact value. Now that gives us one of the tools we could use to help ourselves though. If you were trying to do this and you got this answer in the end and you're like, well, how do I know if this is right? Then we could use this to, you could compare to cosine of 15 degrees on a calculator. So once you got this, what you believe to be the exact value, you could type this expression on a calculator, square root of 6 plus square root of 2, now divide that by 4, and see what decimal you get. And then you could type on your calculator cosine of 15 degrees in degree mode and see if you get the exact same decimal. And if the decimal for this expression matches the decimal of cosine of 15 degrees in your calculator, that gives you confirmation that you did this problem correctly and that the square root of 6 plus square root of 2 over 4 is actually the exact value that they were asking for. Does that make sense?
Yes, thank you.
Yeah, it's a great question. I appreciate it. That's perfect time to think about, not only are we seeing what they're doing with the identity, but you'd like to be thinking about how we would recognize that when you have a problem like this, the identity can be used to do it for you. And thanks for the pointing, Jimmy, thanks for pointing at the fact that the exact value that they asked for is probably the key thing there that says I have to do something more elaborate than, unfortunately, just typing it on my calculator, which would be much easier. All right, great questions, great discussion. Let's see if we can continue. So they have another one, and this one they are in radians mode. And so it says now find the exact value. So we know we can't just type it on a calculator. And keep in mind, we know the exact values when we take sine and cosine of pi over 6, which is 30 degrees, pi over 4, which is 45 degrees, pi over 3, which is 60 degrees. And of course, pi over 2 is 90 degrees, and pi and whole values of pi or pi over 2 we know as well. So those are the ones where we know exact values the same way that I came up with these exact values up above, like square root of 2 over 2. That's the exact value for the sine or cosine of 45 degrees. We know those exact values. I don't need a calculator for an approximation for these things up here in the box. So perhaps one of the ways we can sum up these problems in this section that use these identities that we're looking at so far is that if they ask you for an exact value of a cosine of an angle that's not one of the ones we already know the exact value for, then the question is, can we express the angle that they're asking for as a sum or difference of ones that we do know the exact value for? Because then we can break down that angle into a sum or difference of angles that we know using the cosine of a sum or a difference identities. So in this case, they're pointing out, well, 5 pi over 12 is the sum of pi over 6 and pi over 4. Now, how would you figure that out? Well, if you see that the fraction you have has a denominator of 12, then you can say, all right, I need a denominator of 12 when I'm done. And I know that these three angles I know exact values for. So if you want to see how could I get to a denominator of 12 to get 5 pi over 12 with a sum or difference, I would recommend you convert all three of the angles that you already know the exact values for to all have denominators of 12. So pi over 6, if I multiply by 2 over 2, I get 2 pi over 12. Pi over 4 is 3 pi over 12. And pi over 3, multiplying the top and the bottom by 4, is 4 pi over 12. So now, since they all have a common denominator, I'm trying to imagine how I could add or subtract any of these three to end up with 5 pi over 12. And then you might say, oh, well, that's just the 2 pi and the 3 pi added. And that means I'm going to add pi over 6 and pi over 4, and that's what they have here. So that's how you could set this up to then use one of the identities. And in this case, we'd use the sum identity because I could add two of the angles that I know exact values for to get the angle that I'm trying to find out the exact value for. And then as we see here that once they did that, once they recognized that 5 pi over 12 can be written as pi over 6 plus pi over 4, well, then we can use the sum identity for cosine. Cosine of a plus b is cosine a cosine b minus sine a sine b. So they calculate that with pi over 6 is a, pi over 4 is b, and then using the identity, cosine a cosine b minus sine a sine b. And then each of those we can evaluate. Cosine of pi over 6 or cosine of 30 degrees, as we saw before, is 3 pi over 2. Cosine of pi over 4 or 45 degrees is root 2 over 2. And they end up with almost what we had before, square root of 6 minus square root of 2 over 4 instead of plus. But that's the exact value. So this is example 1b. In this case, they used a radian angle measurement instead of using a degree angle measurement. And we want to try to get used to using either, certainly get more used to the radians since that's the newer ones. Okay. And so now they're going to look at, what the heck? Okay, so now this is, all of these little question marks are degrees. At least that's the way it was before. So each of these is a degree. So now they're going to look at the idea of using the identity in the other direction, which would be nice if they work it out. So this is less prone to come up in a normal situation that you would happen to have this big expression with all these weird measurements for angles that all comes out nice in the end. But nonetheless, let's look at the example anyway. So they're saying find the exact value of, and then they have this big expression where it just so happens that the expression is of a format, cosine A, cosine B minus sine A, sine B. And that's the formula that you would use for the cosine of A plus B. So what they're saying, well, we're going to call this one A and this one B. And then since if we think of it this way, and of course we can only do that because the 93 degrees matches in both places and the 87 degrees matches in both places. Otherwise, we couldn't use the same letter for them. But if we have this structure of an expression that we're supposed to evaluate, and we can see that it fits the identity formula on the right side for the cosine of A plus B, then we could say, well, then this difference of these products can be written as cosine of A plus B, where A is 87 and B is 93 as in degrees. And on top of that, when we add these up, it comes out to be a nice 180 degrees, and we know the cosine of 180 degrees is -1. So in this case, the formula of what you're given is, you know, the expression that you're given is purposefully designed to match a formula like one of these on the right. Well, if they do that, then you can sort of say, well, I definitely need to know, I use the cosine for a sum or difference because it looks just like that expression on the right, and then I can convert it into the left value, which hopefully will be simpler. So then they throw some stuff down here, which a lot of it we kind of know already or don't know, but we could look at it graphically. And so let's take a look at a few of these and see what we think. These are the cofunction identities. Now, already we have this idea of a definition of a cofunction that gave us some of these identities from before, but they're throwing this into the mix because this does help us to re-examine these sum or differences, because remember, the cofunction identities had all of these differences in them. And therefore, they kind of make sense when we're talking about a cosine or sine of differences or things like that. But let's remember sort of what they're talking about. Like, let's say I take a look at this first one. Cosine of 90 degrees minus theta is the same as sine of theta. So why is that? Well, we looked at this back when we were looking at the right triangles. And remember, cofunctions are when you're talking about functions of angles that are supplementary angles in a right triangle here. And so if this is theta, then because the two smaller angles add up to 90, the other one is 90 minus theta. And that's why these were cofunctions, because the theta in the sine here is going to be an angle in the same triangle where the 90 minus theta is the other corner. And so, for example, if I was taking cosine of 90 minus theta, then that would be the adjacent over hypotenuse. So this would be the adjacent to that angle, and this would be the hypotenuse. But then if I flip over to the other corner and take sine of theta, well, now I'm taking the opposite, but they're the same thing. The opposite to theta is the adjacent to 90 minus theta. And so that's why these are equal, because whatever that value of this up and down vertical side is, it's either considered adjacent to the 90 minus theta or opposite to the theta. And in either way, if you take cosine of 90 minus theta or sine of theta, you get that side divided by the hypotenuse, you get the same thing, so those are equal. And I could just do the same thing by talking about sine here, and you could do the same thing by talking about tangent and changing corners. Then you would flip your two sides, and that would give you cotangent, etc. So each of these we sort of knew already. We had cofunction identities back from when we were looking at these right triangles, but now we can also recognize that 90 degrees minus theta is a cosine of a difference. So I could also consider applying a cosine of a difference here if one was 90 and the other was theta, and then I would get to sort of see the same thing would happen here. So if I did that, you could sort of, they're basically justifying that what we knew before from the right triangles come from these angles. Because if I put cosine of 90 minus theta in here, I end up with cosine 90 cosine theta plus sine of 90 sine of theta. And cosine of 90 degrees is 0, so this whole part drops out. And sine of 90 is 1. And so by the cosine difference identity here, you get that cosine of 90 degrees minus theta is equal to sine of theta. And that's the cofunction identity we had from before. So they're bringing these back up now, because even though they're giving them all to us at once, they're bringing these back up now because as we learn the cosine difference sum, and then in 7.3, I'm sorry, in 5.4, we will learn the sine and tangent differences. Basically, all of these could be reestablished at that point. And the same identities can be obtained for real number contain replacing 90 degrees with pi over 2. And so we could do all of these in terms of radians instead of degrees. So they toss these back in our face and then say, all right, here's some more problems to play with. All right, so let's take a look. We have an example 2 with multiple parts. Looking at part A, it says, find one value of theta or x, just depending on which variable they use, that satisfies each of the following. So in the first problem, we want to find a value of theta where cotan of theta would be the same as tan of 25 degrees. So cotan of theta is what is this first one? Cotangent equals 25 degrees. So there's supposed to be a tangent here. So we begin with cotangent of theta is equal to tan of 25 degrees. But one of our formulas from above is that cotan of theta can be replaced with tangent of 90 minus theta. So they use that to replace this cotan of theta with tangent of 90 minus theta. And the reason they did that is now both the left and the right hand side are both with a tangent. And so if we want tangent of 90 degrees minus theta to be the same as tangent as 25 degrees, well, the simplest way that would happen is if the angle inside is also 25 degrees. So that means that 90 minus theta has to turn out to be 25 degrees. And if you solve for theta, you get 65 degrees. And you could confirm that on a calculator, that cotangent of 65 degrees is the same as tangent of 25 degrees. But again, that kind of boils down to our right triangle. So if this is 25 degrees up here, well, then the other angle would be 65 degrees. And cotangent of 65 degrees would be adjacent over opposite. So if this is adjacent and this is opposite, then cotangent of 65 would be adjacent over opposite. But if I take tangent of 25, well, the 25 degree, the opposite of that is A, and the adjacent to that is O, and that's opposite over adjacent, so that would still be A over O. And so this basically is going back to the cofunction properties. When you have two angles that add up to 90 degrees, then the cotan and the tan of those angles will come out the same. So they do another one in a similar way. If you're told that sine of theta is equal to cosine of some other angle, well, the way that I would put it in co-angle or cofunction angle measurements is that if theta and negative 30 degrees add up to 90, then sine and cosine will be equal. And so I would then say that theta and plus 30 degrees equals 90, or plus negative 30 degrees equals 90. And then I would add 30 to both sides, and I would get theta's 120. But they're sort of having you practice a format where when you have an equation equating a sine and a cosine, that you can convert the sine into cosine so that both sides have cosine using these cofunction identities. So they're saying, look at these as a way that you can make a sine into a cosine, or a cosine into a sine, or a cotangent into a tangent, or vice versa, or a cosecant into a secant by just replacing the argument with 90 degrees minus theta instead of theta. So they replace the theta with 90 degrees minus theta, and that converts the sine into the cosine. And then you have cosines on both sides. So for those to be equal, then 90 degrees minus theta must be the same as minus 30 degrees. And if you solve for theta, you get 120 degrees. So this is the same strategy they used in the problem that we deal above this as well. Okay. And now we have our fun old problem. Now everything's nice and clear, and the program is not hanging up, but it's all jumbled. So they're basically doing the same thing here that they did with the tan and cotan, and that they did with the sine and the cosine, but now they're doing it with cosecant and secant. So it looks like they had cosecant of 3p over 4 equals secant of x, because here they've written it out for us. And it says find one value of theta or x that satisfies the following. So we want to find out what x would work here. So they're going to replace secant x with secant of, I don't even know which they're going to use there, degrees, or you could use either degrees or radians. I guess maybe the p is supposed to be pi. I bet this is supposed to be 3 pi over 4. And then they're going to say that that is equal to cosecant of pi over 2, because that's 90 degrees, minus x. So I think this is a pi over 2 minus x. Oh, this is so fun. So that would mean that cosecant of 3 pi over 4 is equal to cosecant of pi over 2 minus x, which means that 3 pi over 4 must be the same as pi over 2 minus x. So that means x is equal to pi over 2 minus 3 pi over 4. And I'd get a common denominator here by multiplying this by 2 over 2. And that would give me x is equal to negative pi over 4. So that's what this is supposed to mean here. And that's the minus is there, and the p is for pi. So yeah, that's what all that jumble translates to with the Teacher Willett translation program. So this is a similar example to each of these, where you just converted from one angle to the cofunction, from one function to a cofunction in order to equate an equation and solve for an angle, which we do in each of these. So 3 of those in a row. Let's see, what's this note? Because trigonometric or circular functions are periodic, the solutions in example 2 are not unique. We give only one of infinitely many possibilities. So that's good. I'm glad they said that as a note. And the way we would see them highlighting that here is that it says find one value, meaning there might be other values as well, but find one value. And so it's quite possible. So in each of these, they said find one value, and then they give you a note pointing out that, well, of course, this angle might work, but because trig functions give you the same answer over some period when you change the angle, there could be other solutions that work as well. All right, so they have like a general idea here, applying the sum and difference identities. If either angle A or B in the identities for the cosine sum or the cosine difference is a quadrantal angle, that means ones that's right on the border of a quadrant, like 90 degrees, 180, 270, things like that, then the identity allows us to write the expression in terms of a single function of A or B, which is what I was illustrating somewhere up here. Sorry to bounce around too much here, which is what I illustrated here. I illustrated here because this is at the borderline of a quadrant, and it allowed us to write this difference all the way down as just sine theta. Or if it was theta, or in this case, theta would have been b, sine of b. So they're going to do, that's what they're talking about here. Let's take a look at what they do with that in the couple of minutes that we have left. So this is kind of like the one that I just did. So when we write cosine of 180 minus theta as a trigonometric function of theta alone, we would recognize that this is by one of those identities, cosine of 180 times cosine of theta plus sine of 180 times sine of theta. And then what always happens when you have something that's on the borderline of a quadrant is that the cosine and the sine are either a 1 or a 0 or a -1 and a 0, so that one of these is going to drop out. So 180 degrees is the same as pi, and over there, The sine is the y value. So sine of 180 is 0. So this drops out to give you 0. Cosine of 180 is -1. And then we have cosine of theta. So that's how this reduces to just negative cosine of theta. All right, so in this example, they're illustrating this sort of fact that they're applying here, and that you could do this anytime. Either one of the sum or the difference of the angles is one of these quadrantal angles, meaning on the border of a quadrant. Then you get a very nice simplification when you apply the sum or the difference identities.